Alright, so this is going to be one way that we can find our zeros, and that is by factoring. So I'm going to first set our equation equal to 0. So my equation is y equals 3x squared plus 9x. Set it equal to 0 because that's what we're trying to find. A 0 is any kind of input value, any kind of x value that's going to give you a result of 0. So that's the first thing I'll do. Alright, now the next thing we're going to have to do is factor. Now remember, there's three things that you have to do when you have to check factoring. Alright, one, is it a GCF? Two, after you factor a GCF, can you go one step further? And usually that's our box method. And then after you do that, then you can go ahead and start solving. Alright, so first thing I'm going to do is I'm going to notice that I do have a GCF. It's 3 and x. So they both have a factor of 3. They both have a factor of x. So my greatest common factor is a 3x. So I'm going to factor the 3x away from both those terms. And what's going to be left is going to be an x plus 3. Alright, and that's still equal to 0. Now, at this point, I'm going to look and see inside of my parentheses, it's just x plus 3. It's not squared anymore, so I cannot use the box. So I'm going to jump straight down to solving it. So I'm going to take each of these factors, which is 3x, I'm going to set that equal to 0. I'm going to take my x plus 3 and set that equal to 0. All right, so we're at this point where I've got these factors, and the reason I'm setting them equal to 0 is I'm trying to find my x-intercepts. I'm trying to find my zeros. All right, so you just solve in each case. So I'll divide by 3. I end up getting x equals 0. I subtract 3 on the other one, I end up getting x equals negative 3. So my two zeros in this case, or my x-intercepts, are 0 and negative 3. So this is one way that we can solve a quadratic, is by factoring and then finding zeros. So we factored our GCF out, didn't have to do our box method. Once we have our GCFs and our factors, set them equal to 0, solve, and you're done.